So if you consider any magnet that should have two poles. In the similar way, Earth will also have two magnetic poles. One pole will appear or it may fall in Antarctica, and another pole will also appear or it will fall in some other region. It is there in our Earth. And let me draw the diagram of that. If we consider this is the Earth, there should be two poles. Since it is in the Earth behaves like a magnet, it should have two poles because a magnet has a two poles. And one more thing before drawing that, I should say something. One more thing, we know that Earth will rotate. It has a spinning motion. It will rotate around its own axis. So let me say this is the axis of rotation. Okay, that is the axis of rotation about which that will rotate. And let me say today we say the directions. We say the directions like the north, south, east, and west. So let's say the direction. Let's say this is a geographic north. Direction of that is the direction of north. Geographically, what we say north is west. It is a consideration. I'm saying that is the north direction. Let me say this is the geographically south. Geographically means usually. Okay, usually if you look at our surrounding, you can say this is our north direction. This is our south, or you can say this is our east or this is our west. Geographically you can say. So let's imagine that this is the geographic north and this is the geographic south. And I told that Earth behaves like a magnet, then it should have two poles. So to explain this, let us imagine that Earth has a giant magnet. It has a very large magnet. But that magnet is not aligned along the direction of this axis. If you consider Earth as a giant magnet, that magnet not aligned, it is not along the direction of this north and south, rather it is tilted, it is inclined at an angle of something. So let's draw it. So this will be the direction of, this is the where the Earth magnet has situated. Okay? So this Earth magnet will form an angle here. Let me call this as theta. Okay? That is an angle. So this is the Earth magnet, and which is inclined at an angle of theta to the axis of rotation. That means to the plane containing geographic north and the geographic south. Okay. And the pole near to the geographic north can be called as magnetic north. The pole of this Earth's magnet, which is near to the geographic north, can be called as a north magnetic pole, and the pole which is near to the geographic south is called as a south magnetic pole. Okay, we named like this. This is the north magnetic pole. This is the south magnetic pole. Now, let me write like this. Now let us say a bar magnet. Let us suspend it free. Okay, we have suspended a bar magnet. We have suspended it, and let's say this is the direction of north pole, and this is the direction of south pole. Sorry, this is the south pole, and this is the north pole. And we know the direction of magnetic field lines, which will from north to south forming the closed loop. Okay, this is the direction of this this magnetic field of a bar magnet. So whenever you freely suspended this bar magnet, it will align along the direction of Earth's magnet. So if you look at here, this is the north pole of the bar magnet, which aligns in the direction of the north magnetic pole. Okay? And the south of the bar magnet, which is aligned in the direction of the south magnetic pole. Understood? And we already know that in magnetism, the opposite poles will attract each other and the like poles will repel each other. See here. Here, north pole is aligned in the direction of this magnetic north pole of the earth magnet, and south pole of the bar magnet is aligned in the direction of the south magnetic pole of the earth magnet. Then, doesn't it repel? Thing is, whatever we have written here, north pole of the earth magnet will act as a south pole. It will act like a south pole. And whatever we have written south magnetic pole will act as a north pole. That is why this north pole will align in the direction of the north magnetic pole, because which is acting as a south pole for this. Okay? And the south pole is aligned in the direction of the south magnetic pole, which acts as a north pole for this. So that is why magnetic field lines of this is from south to north. Okay? The magnetic field lines of Earth is from south to north, because this north pole is acts as a south pole and south magnetic pole will act as a north pole. So that is why our concept is same. Understood? So this is about the Earth magnetic field lines, and this is about the magnetic field lines of the magnet. Okay. And I told you that whenever the Earth magnetic field, magnetic dipole is aligned at an angle theta with the axis of rotation. And let me take two planes here. Let me take the plane here. Let me consider a plane like this. Let me consider a plane like this. So a plane containing, this is the plane I drawn here. So if you wanted to show, let me take the plane like this. This is the one plane. Okay. The plane which containing geographic north and geographic south is known as a geographic meridian. Geographic meridian means it is a plane, it is an area that contains geographic north and geographic south. This is known as magnetic meridian. It is just something plane, that's all. Magnetic. It is a geographic meridian. And a plane which containing the imaginary lines of magnetic field lines of the Earth is known as a magnetic meridian. We have to consider one more plane which is which contains the imaginary lines which is passing through the south and north pole of the Earth magnet. That plane, this plane is known as a magnetic meridian. So if I take like this, see, this is the another plane. This plane is called as a magnetic meridian. This is geographic meridian, another one is magnetic meridian. So as you can see here, I told you that the axis of rotation, this is the axis of rotation, and this is the alignment of Earth magnet, and they are aligned, they are inclined at an angle of theta. Okay, so that you can also see the same angle here, that is the theta angle. Theta is the angle between this magnetic meridian, this plane, and the geographic meridian. So the angle between this magnetic meridian and geographic meridian, it is called as a declination. Okay, we are introducing one term here that is known as declination. The concept of magnetism is very important. Declination. Okay, declination means it is the angle between geographic meridian and magnetic meridian. Okay, see here. Let's say that let me draw one more diagram here. So this is the axis rotation. Now what we are doing is we are taking a magnetic needle and we are going to this place to the center of this arc. Center means on the surface. On the surface we are moving to this point. We are at this point. Now we have this magnetic needle. So what happens when you go to this point? What happens is your needle will align in this direction. Your needle will align in this direction. This is the direction of the axis rotation this side. Okay? And here you can get some angle. Okay? So that is the angle between this magnetic meridian and geographic meridian. So that angle is called as D. Okay? And imagine that you are moving upwards. You are moving towards the poles. As you move towards the poles, this angle will increase. Okay? So the angle of declination will more at the poles. At the poles, the angle of declination is very high. And at the equator, you already, I think you have heard of the equator. Equator means it is a line which passes to the center of the globe or center of the earth. So that is known as the equator. Okay. So equator, when you come to the equator, the angle of declination will be very small, and it will be very high when you go to the magnetic poles. So declination means it is the angle between magnetic meridian and geographic meridian. It is the angle between magnetic meridian and geographic meridian. Now, let us define one more concept that is known as a dip, or it is also called as inclination. Another concept that is inclination. And one more concept we have to discuss that is called the horizontal component of the earth. So here, previous to this, we have defined one term that is called declination. After that, we have to discuss about the dip, and one more thing we have to discuss that is the horizontal component of the earth. So, why we are discussing this component is they will define the earth magnetic field. Or to study the earth magnetic field, we need some elements, and they are known as earth elements. Elements of the earth magnetic field. So they are angular declination, angular inclination, and horizontal component of the earth magnetic field. I told you that they are required to define the earth magnetic field. So that is why they are called as the earth magnetic elements, or the magnetic elements of the earth. Okay. Now let us discuss about the dip or inclination. Now, let us draw earth. This is the earth. Okay. Let me say you are here. Okay, you are on the surface of that earth, and you have a magnetic needle, magnetic compass you have, and for the first time or for the beginning, imagine that you are on the equator. You are on this equator. You are here on the equator. You have at this point you are standing with the magnetic needle. So if you have a magnetic needle, let's say this is the north magnetic pole, and another one is the south magnetic pole. This is the south magnetic pole. And now you are standing here. You have a magnetic needle, and if you have a magnetic needle, if you have a magnetic needle, what will happen is the needle will align in the direction of north and south. It will align like this. Okay, let's say this is our north, this is our south. So I am on the surface of Earth on the equator, and so that what will happen is my needle, the needle of that compass is aligned in the direction of north and south. Okay. Now, if you displace it from the equator, you are moving towards this, then what will happen is the needle will also show the direction of it will try to align in the direction of this, but it will tilt like this. Okay, it will bend like this. So this is actually our horizontal one, horizontal axis. Now it is tilting like this, and it will also align the direction of north and south, so that it will form some angle here with the horizontal. So that is known as angle of inclination. Okay, let's say that this is also north pole of the needle, this is south pole of the needle. You have at the equator, it will align along the horizon. So when you are moving towards one pole, then what will happen is it will align like this. Okay, because you are on the surface, that is why it will be like this. So there will be an angle formed between the horizontal and direction of this is the direction of magnetic field. So an angle will be formed between the horizontal axis and this direction of magnetic field. So that angle is known as a magnetic inclination or dip. Okay. So let's say this is the direct, this is the horizontal one, horizontal HE of the earth magnetic field. This is the, let's say, this is the direction of BE, direction of magnetic field. Okay, it is aligned like this, and this direction of magnetic field making an angle with the horizontal, as I explained you. That is theta there. Sorry, let me write this is I. I means this angle of inclination. So this is the vertical component I draw there. Okay, since it is at an angle of I can write vertical and horizontal component. So this is the ZP is the vertical component. If this is I, then HE can be, with the help of trigonometry, what you can write is HE is adjacent side, hypotenuse side. So that is why HE is equal to BE into cos I. This is the value of horizontal component. And ZE is equal to, this is the cos, if this should be sine, in terms of sine, that is BE sine I. So that is the two components, one is the horizontal component and the other is the vertical component. So let me, before that, let me write a definition for the angle of inclination. If the needle is freely suspended on the surface of Earth, then angle formed between horizontal components and direction of magnetic field of Earth is called D. So it is the angle between horizontal component of the Earth magnetic field and the strength of the magnetic field or the direction of the magnetic field of the Earth. It is known as an inclination R. Okay. Now we got the values of horizontal component and vertical component. So I told you that whenever you are moving towards this pole, the needle will make an angle like this. It will go like this, and when you go to the pole, it will align like this. Okay? When you come to the equator, it will be like this. So this BE will be along the horizon. You have to observe this, you have to imagine this. This BE, this is the direction of BE, which will along the horizon. If you are moving towards the one pole, let me say it is a northern hemisphere means it is a region, that's all. If you are moving to the northern hemisphere, it will go like this. Okay, so the angle at the pole, they will form here 90 degrees. And at the pole, there is no horizontal component because B was like this, and finally it overlaps over the vertical component. That's all. That is why there is no horizontal component. Okay, at the pole, only we can have vertical component and horizontal component will be 0. So at this pole, horizontal component H is equal to 0 and ZE is a vertical component, it is a maximum. It will be maximum. And if you are coming to the southern hemisphere, then it will rotate like this. And when you come to this pole, it will align like this. Again, here you will get a what component? Vertical component. So when you come to the equator, you cannot see a vertical component. This direction B along the direction of the horizontal component. That is why along the equator, HE is the maximum and ZE equal to 0. Okay? So the vertical component is not 0 except this equator, and this horizontal component of Earth magnetic field is non-zero except the poles. Okay, in all the regions there is a horizontal component and vertical component, and this vertical component is 0 only along the equator, and this horizontal component is 0 only at the poles. So this is some of the things we should understand. So let me draw those equations. Let me draw write the equations here. What equations we got is horizontal component. Horizontal component is, that is HE. HE is equal to BE cosine, and the vertical component is, that is ZE is equal to BE sin phi. Okay? Then, when this horizontal component is the maximum, where is the horizontal component is maximum? I already told you, along the equator. At the equator, horizontal component is maximum because What is the angle found here? This is the angle of inclination here. This DE will be aligned along the direction of this HE at the equator. That is why this I will be equal to 0 at equator. Let me write data, some conditions. Okay. Let us take this is equation number 1, this is equation number 2. Let us do some mathematics. So equation 1 and 2, 2 divided by 1, equation 2 divided by 1, so that I can write BE sin I. I am writing this part as in the LHS. B sin I divided by DE cos I. So which gives ZE divided by HE. So here BE cancel out. Sin by cos I is equal to tan I, which is equal to ZE by HE. So using this, you can find out the value of angle of inclination or angle of dip you can find out. That is I is equal to, take the tan to the RHS, so that what you can get is I is equal to tan inverse of ZE by H. So in this way, we can calculate this angle of inclination. And angle of inclination is different at different positions of the earth's surface. Okay, it will be very different. Okay, let us see what happens to this HE and ZE at the equator at the poles. Okay, some conditions. Let's take the equation number 1. HE is equal to BE cos I. Now at equator, one case is at equator, at the poles. Okay. At the equator, this I will be, at the equator, I will be 0. At equator, I is equal to 0. That is why HE equal to B cos I cos 0, 1. That is why H is equal to B. Okay? That means it is maximum. At the poles, it will be like this. At the poles, angle is 90 degree. So at poles, I is equal to 90 degree. Then H is equal to same formula you have to use B cos I. Cos 90 is equal to 0. See here, at the poles, H is equal to 0. And at the equator, H is B, which means it is maximum. And the second case is 2 implies, that is the Z is equal to BE sin I. Z is equal to BE sin I. At equator, I is equal to 0. At poles, I is equal to 90. At equator, Z is equal to BE sin I. While y is equal to 0, sin 0 is 0. That is why Z is equal to 0 at equator. Z is equal to 0. And Z is equal to B sin I is equal to 90 degree. Sin 90 means it is the maximum value. Sin 90 means 1. So Z is equal to B. So this is the result of we got here while discussing the earth elements of the earth magnetic field. So this is about the concepts, like some of the terms that we discussed here is magnetic declination, magnetic inclination, and horizontal component of the earth magnetic